And there's the go live. So now we're definitely streaming. Well, it's going live. Now it says we're live or we're live, one of the two. It's a funny thing about English, right?
This is what makes English the hardest language to learn if it's not the first. That's what I've heard anyway. I've heard other languages are actually easier to master, and English is just difficult because it doesn't really follow the rules. And we are live. I'm hearing us now. We've got a about 30-second latency.
Cool. Yeah, my only other second language is Japanese, and it's pretty straightforward. You toss out the noun and some verbs, and you imply the rest by context, is the way I look at it.
You learnt Japanese?
I used to speak some back in the old Commodore days, yeah. I could get my face slapped in 10 seconds flat in a bar, so I was good.
Bill, you could get your face slapped anywhere in any language.
Yeah.
If you really were.
Oh, back in my day, yeah, absolutely. So, no, I even coined some phrases that there's phrases that the natural speaker just won't put together, but like one is mondai nai, not a problem. And I'll say it that way, and you can tell I'm gaijin by the fact I say it, but at the same time, it usually makes them laugh that, not a problem.
It's good. That's an important one to have, to be...
Well, it was before China was open, so Japanese was the language of engineers, was the way I looked at it. Hey, Dave, good afternoon.
Hey.
So...
Are you able to see the chat there on the tubes? I didn't have it open.
I'm watching the chat.
Okay. I'm going to keep the Discord open.
We've got all of 2 viewers right now, so...
Yeah. So welcome back, everyone. So last week we were talking about instability.
What were we talking about?
No, we were talking about metastability.
That's it,
right?
Yeah.
In Gates. And I'd mentioned that I was getting into, refreshing or blowing out the cobwebs in my head around differential amplifiers, because I think Wes or someone had asked a few weeks ago, could we talk more about OPAmps? And because we mention them every now and then, but they're kind of the workhorse of analog, right?
Right. Oh, hey.
Yeah, go ahead.
Well, I was going to say the OPAmp board showed up, the 6-layer board, so we'll have to do them next week.
Oh, definitely. Here's a funny story. I ordered my my octave up fuzz pedal that I was designing in Fusion that I showed a few weeks back. I ordered the OPAmp boards, and the tracking said that arrived. I'm like, these didn't arrive. They're not in my mailbox. Well, where are they? And then I remembered OPAmp had my address since I was at Altium. So they sent the boards to Altium's headquarters in La Jolla. And I had to on LinkedIn and contact some old co-workers or email them to ask, oh, look, is anyone checking the mail there, and could you get those for me, please?
Oh, what a shame.
And they came back and said, we didn't find them. I'm like, I don't know what's happened to them. I'm still trying to track them down, but I might might have to order them again.
Yeah, I was gonna say, or you see your guitar pedal, somebody else producing it on the web,
Well, they might have just seen my name on it and thrown it in the trash because they're angry at me for leaving and going to Autodesk.
Oh.
But I don't want to be that negative. I want to assume that there are people there who are my friends, so
Right. Now, Drew from OPAmp sent me some Flexboard for a video I was working on for Hackaday.
I didn't know they were getting into Flex. I wondered if and when they would get into that. So that's really good.
Yeah, they do good Flex. Yeah.
You have it there
and Flex,
to
as you know, has great properties, right? Just a little expensive.
It is.
But it showed that it arrived and everything, and I never got it. It was the same thing. And I think Drew even sent me the latitude and longitude or something of the, there's a way to track where it got delivered to. But I think one of my neighbors ended up with it. So I ended up just buying some flex to make the video with, and then I don't know if I can't remember if I did the video or not.
Well, that's something else we need to talk about is flex, because it shows up in a lot of places, and if you can avoid designing with it, it is more expensive than regular PCB material. But if you're making, if you want to design the next generation, tracker device or anything that's small, it's pretty hard to avoid using flex to get things small.
So how do you attach flex? Let's go ahead and talk about it while we're talking. Maybe how do you attach flex to a board? Do you make it as all one piece, or do you have? We used to use the old zebra conductors in the old days.
Right. There's two ways, and actually these displays give a good example of that.
Right. Good view there. Yeah.
So I'm trying to. Where's the camera? There it is.
Yeah, it was focusing. Yeah.
So the flex is actually the LCD, and the chip that drives actually OLEDs, the driver chip is actually flip chip mounted directly on, and you can just see here there's some adhesive covering on this. But this is a flex PCB, and it comes out, and so you can buy cheap, if you need to use flex, you can buy very cheap flex circuits if you're willing to use off-the-shelf connectors. So this is a 50 pin or 30 pin, or I think this one's 50. They have 20, 30, 40 pin connectors and standard FPC circuits. So those are really cheap because they can be very mass produced, But if you're doing a PCB and you need flex as part of your board, like the display has it, coming out there, it's part of the laminate stack up, and so you'll have either a completely flexible board, and then you have to design your layer stack and communicate clearly with the fabricator that you have this master layer stack, and these sections are using polyimide flex material of a certain thickness, and these other sections laminated onto it will be using cores, and that's the reason why it's expensive normally if you're doing low volume. The only reason why is because it invokes multiple lamination cycles. If you're doing a 4 or 6 layer rigid PCB, a 4-layer board, they'll take a pre-clad core and etch. They'll drill, plate through, and etch the core. Then they'll put pre-pregs and copper foil and laminate that. That's for a 4-layer board. So it goes through one lamination cycle, and then they drill, plate, and etch the outer layers. And
so maybe next week I could.
Lamination.
I was going to say maybe next week I can show the Aldium example.
Yeah, if you want. And so what we're really talking about is if you're laying up a flex stack up, now you're introducing multiple lamination cycles possibly to the process, and each one of those adds cost quite significantly, because the lamination press, you're talking about many tons of pressure at high temperature and for like hours. So just to make one PCB panel could be in a lamination press for several hours at a time when it's being laminated. So the fewer lamination cycles, the better in terms of cost anyway. Yeah.
Yeah, flex as a part of a PC board is kind of after my time. Like I said, in the old days, we used connectors to transition to flex connectors, or we used to use what we called a zebra connector, which was a conductive isomer poly. I can't remember the words anymore. But basically, you could lay it down, and because its width was so much skinnier than the trace width, it wouldn't short out. They're like rubber, they're elastomer, and you just compressed them, and they would automatically connect this conductor to this land, this conductor to this land, and they were skinny enough that they could land anywhere and not short out.
They have is the right word isotropic? No, it's yeah. They have an isotropic.
Well, I was gonna say.
So it's like the way that they're made is this silicon rubber with carbon impregnated.
I thought it was an elastomer, but yeah.
Yeah, but they make it conductive, but it's only conductive in one direction. Because
this was conductive strips. That's why they called it zebra. There's conducted, not conducted, conducted, non-conducted.
Oh, okay.
And you laid that down and pressed it, and it would connect the land to the flex for you under pressure.
Yeah, and I've seen these are used in liquid crystal displays even still.
I was doing and you mentioned a flip chip. I was doing chip on board and then carting it off to an LCD, and so I was doing a zebra connector to the LCD flex.
Yeah.
So you want to talk about chip on board a little bit? What you mean by that, or flip chip?
I mean, I've never designed that, but I know what it is.
Yeah, it's just basically the chip itself. What's a good way to describe it?
Well, so you have the silicon wafer. You have the wafers cut into die.
Right.
Yeah. So you have your silicon die, and that has to be packaged somehow. So
yeah, you need solder bumps to that it contacts then to flip it. But you don't need a die carrier. You're putting the die right on the board, and so back in the day, that was like, that was our heavy metal way of doing mass production, was get rid of the whole chip frame, the chip package, and put them right on the board. And you can see them on LCDs to this day. If you see a round goop of epoxy, there's a chip under there that's been attached directly to the board typically.
But in some cases, so yeah, this is a whole miniaturization and multi-chip module and hybrid electronics sort of topic, but the Pentium 2s I think were done this way as well. And the Celerons, the first generation Pentium 2s and Celerons, and probably other chips since then too, but the die was bumped with solder bumps,
right? And
then that was soldered onto a printed circuit board, which was the actual chip package, which I guess nowadays the favorite word to call that is an interposer, but it's really it's another PCB between your PCB and the actual silicon.
Right,
but
and it's got decoupling caps on it and stuff too.
But that's what most BGA packages are those as well.
Right,
it's actually a printed circuit board, maybe up to 6 layers. I think they're experimenting with new other types of substrates in recent times, but chip on board is where you can even design PCBs now where you might get a single gate inverter or an oscillator, and they come in these tiny bumped packages, which are wafer scale, and those are essentially just the silicon, and they've got solder bumps, and they may have only 4 or 6 or 8 balls under them, and they're really, really tiny. They're smaller than an 0402 sort of resistor, but it could be a whole chip.
Not for the faint-hearted. That's for heavy-duty mass production, I'm assuming.
Yeah, I mean, I suppose if you have a good reflow oven, you can hand prototype those things, but you need a good.
It's alignment. Yeah,
you need a good
alignment's
magnifying
where
glass.
I have a problem.
Yeah. Or even better, you need a decent stereo microscope to work with to do prototypes.
Well, I have one of those, but the problem is that when the bumps are underneath the board, I've experimented with putting silkscreen around it, but silkscreen registration's so sloppy. Yep. But how do you align it when you can't see the bumps and the land patterns that you're trying to align to?
You actually have to trust
that's why pick and place.
Well,
you're right. You have to trust surface tension to pull it in.
even pick and place machines are not that accurate, especially if you speed them up. It's
another mass production technique.
It's actually something that it really didn't dawn on me until I actually did an IPC reworking soldering class for BGAs.
Okay, that must have been cool.
When I started working at Altium back in 2004, they had this guy come in because we had all these prototype boards that were FPGA boards. They had Xilinx Vertex 2 Pros and Vertex 4s and you know, Stratix 3s, I think. Altera.
Right, Stratix is part of
So we had these very expensive FPGAs. They were $1,000 a piece at the time.
Right,
and
right.
we were prototyping these modules that would go into the nano board to do different things. And so they had this guy come in, the hardware team had this guy come in and teach us all how to use a hot air rework station for BGAs. And we all went through the exercise with these chips. And it was in that class that the IPC instructor sort of helped it dawn on me that it's actually, during reflow, the surface tension of the solder is what pulls everything magically into alignment. And it really does.
Right.
It's quite amazing. Even if they're off by 30 degrees or something, as soon as those balls start to melt and the pads are properly wetted, it'll suck it right down into the right spot. But there's also, you know, risk of bridging if you're way off.
Right, right.
Or
and I still tap the board. I still tap the board to like kind of help that process, and I do that almost subconsciously. From the old days, we would get it hot and tap it, give it a wrap, as we said.
Yep.
So, well, that's cool. And there's a whole bunch of BGA rework information out there. I was surprised to find for people at home because they were reworking their Xboxes. They would get tearing red, and that was all caused by black pin, I think.
Yeah, I heard about that. That there were people were pulling their Xboxes apart and just even putting them. Some people
hair dryers.
They would put it in their oven.
Yeah.
On a tray, and heat it up, and basically use your household oven as a reflow oven. And
not recommended.
No, I wouldn't either, because you just don't know what chemicals you're releasing into your breathing space.
Right.
But yeah, they were doing that, and then it would work again. That's what I'm
and
sure
it was
a lot
bad
of people
enough.
Just screwed them completely doing that too. But
yeah, and I didn't see anybody that admitted that, but I was amazed at how often the symptom was repeatable. Whatever that symptom was, people are like, "Do you have the red screen thing? That's the black pad of the BGA part being used." And I mean, they're even calling it that, which, as we know, black pad really is a thing that can happen depending on, circumstances.
Yeah.
So it's a. So what you got there today? Go ahead.
Just real quick. So just to taper off on that, on those chip on board. Of course, the other way to do it is die bonding. Wire bonding. But you need an expensive wire bonding machine to do that. So I think
we used to hand bond at MOS back in the 70s and 80s. We had a room, and you could peer through the window, and there's these little elderly women sitting at microscopes, and they're hand bonding. And I had some chips hand bonded special because we had to rotate the die like 45 degrees. And these women, they hooked it up. I mean, without shorting the wires together and stuff.
I wouldn't trust myself to do anything smaller than a battery pack.
Yeah, I mean, can you imagine hand bonding a chip?
I went to the trouble of hand bonding this. So I have this old Dell workstation, and the battery it got to 0, would not keep a charge. So I pulled the whole thing apart, and I thought I can replace those. And so I thought surely there's some way to sort of reset the BMS. And so I got a motorcycle battery, and I made a what do you call it, a spot welder. and I
Okay.
got some nickel wire, and I rebuilt this whole thing, and it came out beautiful. And then I'm looking at the BMS, and if anyone watching this show knows, like, and has advice for me on this, I'd appreciate it. I can see that these batteries are full and they will charge. They're brand new cells, and I can bootstrap this by shorting out 2 of the pins on this connector, and the 12 volts will come through. But this chip right here is what's called a gas tank chip. So it's basically it's probably actually under the hood, it's probably an MSP430, but it's a TI chip that's specifically for BMS. And this one is a part number that was OEM'd to Dell. So it's not a generic one. It's part of a family. And I can't get this to tell the laptop that these are new batteries and they have full life. So it still will not. Will not.
And
it'll run.
And
off
if you
the
figure a
battery
way
just
to
long
do
enough.
that, you'll probably be in violation of the digital millennial copyrights thing. You know how
Oh
they're
my
doing
gosh.
that these days.
Yeah. So I'm thinking, well, is there a generic equivalent I can desolder and put on here? No, but no. Dell actually did a deal with TI, obviously, and they made sure that it was hard to reverse engineer or aftermarket or reuse these things. But so I had to go buy another one because other people have done this. They just the companies making aftermarket batteries, they just have their own BMS board on there.
Right.
Now
is that nickel metal hydride or are those lipos, do you think?
These are lipos.
Okay.
Or
as I like to call them, fire starters.
Yeah. Ticking time bomb.
Yeah, because it really takes an intelligent circuit to charge LiPo safely. You don't just, it's not like we charge lead acid batteries where you give it a voltage or current. It has to monitor the impedance of the battery and watch what it's doing and things.
And yet at the same time we can use them as like a giant capacitor if we have an electric vehicle. We can, if you do have a good charging circuit, you can dump tons of energy into them really quickly.
How fast do like the Teslas charge? I thought they're like 20 or 30 minutes.
They can be.
I don't know.
Fast, but just think about this: every time you're going down a hill and you brake, suddenly you're charging the battery.
You're charging your battery, yeah.
And you're charging them very, very fast. And I sat in a prototype electric vehicle several years ago. This guy who actually ended up going and working for Tesla and their truck program, and he's since moved on to drones. But Father Joshua Resnick, he was he's someone I should try and track down and get to talk on this show because he's a super interesting engineer. So he's a power electronics specialist, and he was building an inverter for electric vehicles, mainly for the fishing industry, for boats, up in Kodiak, Alaska. And I went up there and interviewed him for a video some years ago, and he took me for a ride in this electric car he and some local youth had built out of an Eagle Talon. They'd electrified the car, and seriously, the control prototype system in the back was a Labview computer with a breadboard. Right. Seriously, the gate drivers for the IGBTs were all on a breadboard in the boot of the car.
Yeah, and the boot being the trunk for you people from our hemisphere.
Yeah, the trunk. Yeah. So that's the Coriolis effect in effect right there.
In effect. Well, is it effect or affect? Yeah.
I don't know. Yeah, but we were looking at the voltages and currents while driving the vehicle, and we're talking hundreds of amps, or over 100 amps while braking. You're recharging those lithium cells. It's pretty crazy. Right.
Yeah, the I don't know as much about the electric cars as I should. I see their chips because I still read just chip catalogs in general, and I'm watching the 48-volt controllers and all those, and they're huge versions of what I'm used to working with. You know, you look at a chip, you're like, oh, 48-volt controller for 1,000 amps or something, you know, some ungodly amount.
Yeah.
The controller, for the FETs for it.
Well, I know
So.
that reminds me too of coming back to wire bonding. I saw these wire bonding machines, but not for chip to board bonding, for actual wire bonding of large high current cable assemblies. And they had IGBTs, insulated gate bipolar transistors, for those new to that acronym. They were this big,
Right.
for providing a massive current pulse. They're like, it's one transistor is they're thousands of dollars each, because there's a lot of silicon in them and a lot of
It's a lot of, and they do tricks to
protective
make
stuff around it.
surface area in there. They make the shape so that the gate and the source and the drain are as much in contact as they can, but yet a single punch through of that insulative material you're talking about makes the whole part trash.
Yeah.
Makes it into a heater.
Yeah.
So it's
pretty
yeah.
wild.
You mentioned Labview. For people that don't know, that's a cool program that costs more than most people can afford, but it allows you to write quickly and actually run in real time, near real time. So that's cool that he could actually make it run, real time for controlling the car.
Yeah.
So-
It was kind of impressive. Yeah.
Yeah, you mentioned a spot welder. I have a spot welder in addition to a MIG and a TIG, and I was thinking about doing a Hackaday video on welding, but it has to be summer for me to do that, because all that kind of stuff gets shoved in the garage and you can barely walk through it during the winter. But during the summer, maybe I'll do something, show the different welders.
Oh, you should.
Also, I have a plasma cutter. That's one of my favorite things.
What do you
Dangerous as
do-
hell.
I bet. What do you do with the plasma cutter? What?
Well, I was
takes the
restoring.
cut with the plasma cutter.
I actually was cutting steel, but you can cut aluminum with it also. But I was restoring an old Datsun 280Z that I have, and so I taught myself how to restore a car with all the tools that I used to restore it. So I learned how to do body work and how to shrink metal, which is cool. You know, how to heat the metal up and then use a head that's got teeth on it, and it gathers the metal as it impacts it. It shrinks the metal and pulls it. Or you can heat it up and then shrink it suddenly with a wet cloth, and it'll pull the metal to it. Because that's how, when metal's oil canning, there's too much metal there. So how do you make the metal go away? Well, you have to shrink it. And so I had to learn how to, and it takes patience. And I also had to learn patience while doing this. But yeah, you want to learn patience, do some body work. That stuff will numb your mind, the sanding and whatnot.
Yeah, I always thought gardening, pulling weeds is something if you need to grow patience, but maybe body work would be worse. I don't know. At least
Right.
you
Right.
see what you're doing immediately. So.
Yep. All right, so that was a good tale into what you're working on this week.
Oh yeah, so
Or
I'm
what you've got
trying
here?
trying to reproduce here a classic OPAmp, because again, Wes some weeks ago had asked the question, like, could we talk more about OPAmps? And I keep making promises that we'll discuss them, but this is a classic design of an audio OPAmp that's used in a lot of high-end microphone preamps and mixing consoles. It was from the 70s originally, and it's still used in a lot of studios today, but they aren't using OPAmps that you just go buy from TI or whatever. They're actual discrete OPAmps made with separate transistors. And I don't know if this is too fuzzy, this view, or if I should change to the light background, but
You try the white background if it's easy. If it's not,
I will.
don't worry about it.
I will. I normally have the dark background because my eyes get tired real quickly while I'm designing. So So let me just see if I can switcheroo that.
Back when I started, we started on Mentors, and you didn't have a choice. You had a black background, and you could do things like choose the color of buses and segments. And so I still use my Mentor colors I learned some 35 years ago.
It made sense back then because half the users may have been on monochrome or non-color displays, and you still have to have good contrast even if you're on a green or amber colored screen.
Right.
So
we had a couple colorblind engineers as well.
Let's go white. Background PCB schematic white. Yeah, I'm still learning my way around this.
Oh, cool.
That's probably a bit easier to look at. So first thing you'll notice about an operational amplifier is they're always DC coupled. So if you look right through, these are our inputs, the non-inverting input here, the inverting input here, coming into this differential amp stage. So we'll talk about diff amps.
Whoop, did I lose you? You froze. You're there. You're back. Okay.
Right. So diff amp, the input stage DC coupled. We're DC coupled all the way through. There's a second differential amp stage here. Also DC coupled all the way through the signal path. So an operational amplifier is only called an operational amplifier because one of its characteristics is it can be operated for mathematical operations. So by that we mean multiply, divide, add, subtract, integrate, differentiate. That is why operational amplifiers are called operational amplifiers, because they're for mathematical operations. So if you think about it, op-amps existed even with vacuum tubes in the 50s. There was I think they're called Fillmore. If you can find one, it's a collector's item now, of course. But they had op-amps made with two twin triodes, so two 12AX7 tubes, and with those four triodes, you could have an input long tail pair. I'm in the habit of calling them a long tail pair. I don't know who coined that phrase or where it came from. It's just what one of my mentors used to call them. So, but a diff amp with two triodes, and then that would go to a second triode as a voltage amplifier gain stage, and that's where the diff amp and the second stage is where all the gain comes from. You need lots and lots of gain. An ideal op amp has infinite gain, but of course we know that's not real. But we get as close to infinite as we can, which means so much more gain than the overall system needs, because then we can control it. And then the final stage is a buffer, because high voltage gain stages typically don't have a low impedance, so they can't drive heavy loads, right? So you need an output stage. So here, this one has two differential gain stages. The input provides high impedance and a differential input, which is what we need for creating circuits using feedback principles. So you need an adding input and a subtracting input is what that really boils down to. Then that goes to a...
Whoop, lost you. Keep talking. Keep talking. Still don't have you.
The drivers for the... It's actually, the third stage is really the drivers for the output stage to help bias the output. These output transistors are typically higher power and can drive more current, and they're in a push-pull, but you get crossover distortion. If the signal starts to go positive, this Q8 NPN transistors conducting more, and then the signal goes to 0 and then goes negative, Q9 starts to conduct, and that crossover point in the middle, in this kind of push-pull configuration, can go flat as one transistor turns off maybe before the other one starts to turn on. Right. So this whole previous stage is really a servo for biasing them on to remove that flat spot in the middle of the waveform. So the diff amp we have on the
You're going to have to back up about 10 seconds. We're losing you again.
Hello.
Yep,
Why
there
does
you
this
are.
always happen?
It's probably lined up with your kid's class, I assume.
No, I don't think anyone else is on a Zoom right now. I just think AT&T wants more money from me, so they just
that could be, yeah.
Choose to make it hard.
So we got it up to, you explained the flat part on it, and I think we got most of what you said there.
Yeah, so the stage just before the output is a bias servo, or it does biasing to make sure the output transistors are just slightly turned on.
Right.
So you don't have that flat spot, the crossover distortion.
Right. So in an unrelated thing, in Schottky and digital, they bias it so that they never get saturated. They try and keep it, it's digital but not analog, but yet biasing is how we get the speeds out of Schottky. So the circuitry that goes around a transistor is the juju. The transistor does the lifting, but it's all that stuff around it that makes it usable, in my opinion.
That's right. So we're sacrificing efficiency for performance there, because you don't want logic circuits with the transistors, like you said, Bill, you don't want them saturating. So what is saturation?
You're asking me? Saturation is where an input change no longer results in a linear output. You can keep piling electrons into the flow, but it's no longer amplifying that. It's just more charge you have to remove when it's time to shut it off. That charge that you dumped in that bucket has to go somewhere, so you got to pull it all back. Instead, what you wanted to do was put just enough in there to get the result you want, and then stop adding to the bucket.
Yeah. So the transistor's on as hard as it can go, and you can't make it turn on anymore. The valve is fully open, and adding more current into the base just wastes heat. But to your point, it also adds when your transistor's in a saturated mode, it's harder to turn it off again. Right. And so that slows the whole thing down. The transistor may be passing a lot of current and have its minimal on voltage, so it may be dissipating less heat. So saturating a transistor might be appropriate if it's just turning a relay on, or a light bulb, or a heater element.
You're absolutely right. Getting the charge out, it's like a bathtub. You can control how much water you put under pressure into the bathtub, but when it comes time to drain the bathtub, it's just kind of gravity and the width of your drain that works, and you have to wait for it to drain out.
Yeah. So there's a whole science to that, even in power supplies. You were talking to me before we started transmitting, before we started the stream. You had a different switching power supply book, but there's this whole art and science to gate drive in switching power supplies, because you want to do the same thing. You want to minimize loss in the switching devices, which means turning them on as fast as you can and turning them off as fast as you can. But you also have to trade that off against the lower channel resistance, if it's a MOSFET, during saturation, or low forward bias voltage drop if it's a BJT transistor. When you're in saturation, if it's just DC going through it, you're minimizing the loss. But getting them to turn on and off quickly,
right,
and get just to the point, almost to the point of saturation, but not quite. So it's pretty tough. Gate drive can be hard to do. I think that's why a lot of the semiconductor companies have come out with dedicated gate driver ICs that just drive the power MOSFET, and they can actually, some of them can even take feedback. They connect across the channel of the MOSFET, so they can essentially measure the on resistance.
Okay.
And the on and off switching characteristics on the fly in real time, and keep it just at that right level. But yeah.
Right.
So what's that?
I was going to say, this is, you and I were talking about this, and every now and then there's a book I'll recommend, and this happens to be one that sat in my bathroom for a couple years. And it's just a Switching Power Supplies A to Z by Sanjaya Manikat. I can't even say it. Maniktala.
The point is, it's a Nunes book. Nunes generally has really good engineering books for electronics.
Right.
I've found.
Right.
I've got a few of the Nunes books too.
Yeah, I just opened it to a section on feedback loop analysis and stability. They go in very carefully into the PCB topology. Here's the math of PCB traces, stress, reliability, life. And what I used to say about being a designer was, it was one thing to be an engineer, but then there's topics that you need to specialize in before you can design using it. I used to call getting your card punched. For example, my card used to be punched for microprocessors, right? I could design with them pretty easily. My card is not punched for modern switching power supply design. I mean, I understand it, but I would have to fill my head for weeks, if not months, with everything. If somebody said, build a power supply, a true switching power supply, or specify one that can go up on the shuttle, I'd be like, okay, I got some work to do.
Well, come on, but even in that example, though, let's be fair, even a power supply expert who works for JPL would have to spend weeks for each new product to research it, to also make sure it's going to work in space.
But only weeks. Yeah, I should have said years. Yeah, for me, it would take a year to load up what they could load in a week or a month or whatnot. So yeah, the amount of man hours. Yeah, it can be real. The amount of man hours that can go into a design isn't evident just by looking at the electronic schematics sometimes, because it is the physics of the components used as well as how they play together.
Well, it's one of those things.
Just happened to.
Actually, that's an interesting point. It's one of those things. If you look at a design, if you look at the schematics of somebody else's design,
right,
you can say, I know what they're doing there. Like, you can look at it and go, that makes sense to me, because that's what schematics are. They're a communication language for electronics.
Right, exactly.
And you can look through something like this OPAmp circuit and go, like, I had a double take on the output stage, because the PNP transistor is driven on the collector of this.
I did the same double take. Yeah, I did the same double take.
And the NPN is driven from the emitter. So this is an emitter follower stage driving this, but this is a common emitter stage.
Common emitter.
This one.
Yeah.
But the reason is this transistor more forms part of the biasing network and a current source. So if you think about this as just a biasing current source, which is mainly what it is at DC conditions, then really we have this one transistor as a kind of differential drive for driving the output stage. And that is actually how this OPAmp operates. But not all of them would operate with the same mode of operation. But you can go through something and you can basically think about it and go, yeah, in my mind I can look at that and analyze what's going on. And with the tools of circuit analysis under your belt as well, like this semiconductor circuit analysis, you could even isolate different chunks of the circuit and find out what's going on. But
Right.
to do it starting from zero, that's the genius, right? That's when you look at some people and go, that person really knows their craft. That power electronics designer really understands switching power supplies, because I can go to him or her and say, I need 17.2 volts within 1%.
With a certain efficiency, yeah.
With a possible loading, not including
regulation.
open circuit, possible loading from 2.2 to 2.8 amps, and it has to respond to the load this quickly, because loads can change, right? So you might, and some power supplies the power supply is also a feedback system that has damping, and so if your load is changing too rapidly and the supply is underdamped, you'll get brownouts.
Right.
Like it won't stay in regulation. Or if the supply is
it could oscillate.
It can oscillate, yeah, and the whole system can fail like crazy. So you go to someone and they say, okay, I can do that for you, and then they go away and they pick some topology, and they come back 3 weeks later with a prototype for testing, and it's some kind of CPIC, super efficient, tiny little magnetics, and yet meets the spec. It's like, that's the genius when you that's what you want to aim for, and you kind of do need to specialize. I haven't specialized that much. I did study. I convinced my university to allow me to do the power electronics classes when I was doing my computer systems engineering degree program, because I've always been fascinated particularly by power electronics. Ever since I discovered the Class D audio amp, I'm like, that's a power supply with an audio input. What?
Right. And I remember what got me where I thought, hey, I actually may know some of this stuff. My boss tried to make a voltage splitter using an OPAmp, and then he hung like 100 microfarad cap on the output. And I went, excuse you can't do that. You can't hang capacitors on OPAmps. And he didn't believe me, and he had to find out it didn't work. And it's, and that's one of those things. OPAmps aren't real tolerant.
Modern op-amps have gotten a lot better, I've got to say it.
They're better now. They absolutely are.
If you want to, and that's why you look at op-amp data sheets for some of the more expensive ones from ADI and TI and Microchip, they almost always state on the first page, this drives capacitive loads well. And that's why.
If they do, yeah.
If they do.
Yeah.
If they don't, watch out. Oh, the other gotcha with op-amps that really bit me on multiple occasions was, particularly in audio. Okay, so I designed a preamp, an audio preamplifier or equalization circuit or filter of some kind, but I want super low noise and low distortion. So I'm searching the lowest noise, lowest distortion op-amps available, and I get that to get very low noise, they have to use larger silicon. You have it's about statistical models, right? But you can have a greater area in a MOSFET or area in a BJT, and it will increase the biasing current. You need more current to keep it in its linear region because it's a physically larger chip.
Right.
But you get much lower noise and lower distortion by doing that. So all the good audio amps and op-amps use large input long tail pair transistors.
So the ratio of the bias current to the noise current that's just there from heat and Brownian motion and stuff, the ratio gets better then, I assume.
Yes, it does. And also you're reducing the noise in your surrounding biasing circuit because you're using lower impedances. So you have less shot noise as well.
Less influences.
What the heck is someone trying?
Your phone's buzzing.
I'm always getting, and that's my camera, so it's making it fuzzy.
Right.
Why do people
Well,
always
it's
try to
funny.
call me?
I mentally was going, we could apply an FFT circuit to your picture and remove the frequency of the buzz because it was an actual 2D artifact in watching you, the buzz. It was pretty funny.
Oh, that's funny. We could totally do that. So, yeah, so they're more expensive and they have higher current requirements. But what I didn't get was also to get super low distortion, you need a lot of gain. And a lot of gain means a lot of gain in these internal high gain
Open
stages.
loop gain, yeah.
The higher open loop gain causes difficulty in design for stability.
Right.
And so a good, and there's the notification giving you the cat.
Well, I'll just pull up the schematic while you're. Hi,
I'm
Kitty.
back.
Up, you're back.
Albeit pixelated, I think. The cat keeps. Why are these people notifying me all the time? Anyway. Don't you just feel that sometimes you wish the whole world would leave you alone?
I don't grok cell phones. I just don't. I mean, I did originally. They were a godsend. I used to, I could tell you cell phone stories, carrying them on the ambulance, and people thought we were magic. And yet I'm not into it. I'm not into texting and being texted by people I don't know. It's just which makes me officially a dinosaur because everybody uses their cell phone. That is the next step for, like, you watch The Expanse. They're carrying fancy cell phones around with them.
Oh, I love
it's
The
just
Expanse.
theirs are better
What a great show.
design.
Yeah.
Well, hey, there's a great series on YouTube by Adam Savage where he goes on the set of The Expanse, and he's talking with the special effects guy. So he's right in his home base, right? And there's things that I didn't realize is like the little hand carrying computers they use a different backlit color depending on whether they're from the Martians or whether they're from the Belters, or so it was a lot of cool stuff that because I'm a big Expanse fan. I read the books originally, but yeah, watch it. So if you get a chance, check out Adam Savage's channel and or Google him for The Expanse. It's pretty cool.
I will. I'm definitely going to check that out. I love The Expanse. So yeah. Where were we about that? Yeah, stability.
So open loop gain, though.
So yeah,
we need lots of it.
We do, but one of the difficult things is making an OPAmp stable. And so you'll notice in this particular one, there are a couple of capacitors here. I forget what these are on the long tail pair. I did know the theory of those and why they help, particularly with microphone inputs.
Okay.
But I'll have to come back to you on that.
What do you call in the long tail? What is that? Is that the front
differential
end?
amp? This part.
Yeah.
It's called a long tail pair. But that's just slang for diff amp. It's a diff amp, a differential amp. So if you think about it, but anyway, I was talking about stability. So that's why this 47 picofarad capacitors here, it's a kind of feedback. This is in a kind of negative feedback inside the OPAmp circuit.
Well, the old OPAmps, we had to bring out the equalization pins. Remember the 741?
Right. That's right.
Yeah.
So these are called frequency compensation caps.
That's right.
And those increase stability for high frequencies. And I didn't get that when I first started reading about OPAmps and they were talking about stability and needing frequency compensation. I just thought, well, it's super high gain, so you don't want it to oscillate. Well, yeah, that's only the first part of the story.
Right.
What people need to realize, and there was a good article by one of TI's applications engineers on this, and you can see it, your OPAmp may not break into random oscillation. It might if you design your circuit with not the right gain and phase margins. You may create an oscillator accidentally. But where it really shows is damping. If you have an OPAmp with a feedback loop and you're making a filter or something, if you put a square wave pulse through that and look at it, you may see ringing, lots of ringing on the high and low transitions. and that ringing is a sign of high frequency instability. And the thing is, there's such high gain in some of these op amps, particularly low distortion, low noise ones, that I was buying these op amps from New Japan Radio for audio purposes, and they just even in the circuits I was using them in, they just didn't quite sound right. And there were two things I forgot to look at.
You could hear a difference, huh?
I could, but there were two things I forgot to read or pay attention to in the data sheet. One was this little note in tiny text at the bottom of the page that said, "Do not use this op amp with in circuits with a gain of less than, such and such dB, like 30 dB." Huge amount of gain for an audio application.
33 or something like that, yeah.
30 dB is what you need if you want to take the output of a microphone and make it line level kind of deal. Like, that's a lot of gain. And I'm like, why not? Because I had a circuit where I could dial the gain back to 1 and go between 1 and...
A lot of things aren't stable at 1, yeah.
And at 1,
Unity.
it just... And I thought, oh, that's a problem. But then I could fix it by putting a capacitor and making it kind of like a low-pass filter, but putting a capacitor in the feedback loop would actually eliminate the instability. And it's all about the gain and phase margins in such a high gain op amp. And the difference between that one and some slightly more expensive ones, like the LM4562, for example, is they put a big capacitor inside the package and include it in the op amp. So they've pre-compensated it internally for the high gain, and so it'll work down to a gain of 1, no problem, without the ringing.
Yeah, that's counterintuitive that it's harder to do a gain of 1 than it is to do a gain of 100. But
it is.
That's and maybe we can talk about error gain and stuff, gain error next time. We're actually coming up on the top of the hour here. I do have a question. Somebody asked if long-tail pair was from MIMS. I think you just said your mentor used the phrase.
It could have been. I don't know if Forrest Mims coined that phrase or if it's, but it was my friend Richard Freeman in Australia. I hope he watches us someday. I don't know if he knows we're doing this. He's a cool guy. He's actually, had a career in networking, much like you, Bill, but he's always been into audio electronics, and he taught me a lot of what I learned early on.
Right.
And that's just what he called them.
Right. So in theory, only 18 people know we're doing this, so we should probably start putting the word out. Now we have the tech issues worked out of this thing. And I was interested maybe if people, if you're a part of the Discord channel, which you can get to from going to Coriolis-effect.com, and I'm not going to spell it today, but there's a Discord invite there on the menu. If you'd like to do a Skype in sometime and show us one of your projects or something, maybe that's something we can do on a semi-regular basis.
Yeah, we should. We'd love to do that. That would be awesome.
So yeah, Mike Fikes just got his TDR and he hooked it up to his TEM cell and stuck his hand in it, and that'd be like a cool thing to see live, So. Yep. Any other questions about op amps from anybody while we got you? True unity gain op amps are quite difficult to get right. I tend to agree with that statement.
They are.
Yeah, and then there's gain bandwidth product. Those, which is way simpler than it sounds, but yet more complicated than once you do the math.
Yeah, so you had a gain bandwidth product graph up earlier before we started, I think. Do you still have that there, Bill?
Let me see if I can find it. It'd be too hard for me to pull up right now because I think I replaced it with your desktop once we started.
Okay. Well, like I said, when Wes first said, could you guys talk about op amps? I'm like, we could do a whole year on op amps. There's so much to it. They're amazing.
Right. So yeah, I'll cue those for next time. Geez, boy, that hour flew by, didn't it?
Sure did.
You thought I was kidding you at first, didn't you?
I'm like,
so yeah, I'll have to, like I said, I'll have to stick some. Oh, another old book we had talked about. I dug out. We'll have to. Oh, there was a transmitter. It's always a danger for me to open these and start flipping them because I forget where I'm at. And I start wanting to read them. You know, once I see a circuit. Or don't your eyes, when you see a tube in a schematic, your eyes just go to the tube to see what it's doing? Yeah,
absolutely. That looks like a power supply. That was
yeah, it was.
Power supply.
Yeah, I saw and that looks like a receiver.
Yeah, with a push-pull output stage at the end there for driving.
Oh, it's a transmitter. Yep.
Oh, it's a transmitter.
Yeah, because you said push-pull output stages. Yep.
Yeah, that's interesting because I would have thought most transmitters back then would have just had a single tube pulling a resonant tank that has the antenna coming off of the tap. Right. Yeah, and it's got a we used to call those Siamese triode, where it's got the same cathode. Yeah. Anode. I get my A's and C's backwards. I actually did that the other day. I was trying to remember A from C, and I do it by remembering electrons and building up from there. And the young Bill Hurd could do that in a couple nanoseconds. The older one has to take a coffee break halfway through that whole exploration of where electrons come from and where do they go once you're done with them. Get rid of that pesky charge. So, very good. Well, cool, man. It was good talking with you. I do have something scheduled. We're going to measure those next week, aren't we? The 6-layer board?
I'll try and solder them by next week and then maybe measure them by the week after. How's that?
Okay.
I'll throw them on the TDR.
Right. Meanwhile, I'll track down my missing fuzz pedal boards and see if I can get my hands on them and get those built. Cool, man.
You got to demo them once at some point.
I will. When I'm ready, I'll play something, but I don't want to bore everyone with my strange musical taste either. So
all right.
I'll just do a smidge. How about that?
All right. Well, thanks for everybody that watched, and tell your friends, that we might actually be able to do this on a regular basis. At least statistically, we're getting there. So we'll see you next week, same time. We might even, Bill, just throwing the thought out there, is just planting the seed. We might even give away some cool stuff to people if here and there. Because I got data books.
I got a lot of interesting things. I'd gladly send them to people who want them if you bring your engineering friends along. Right. And I'm into good homes for stuff. I want to know that somebody's actually going to use it. Me too. Absolutely.